Okay, let's talk about velocity now. If we remember, we had a definition for average velocity, and we said that was equal to the total displacement over the time interval. And we've seen this as maybe delta x over delta t before, and that gives us an average velocity. We need to know a final position, an initial position, and the change in time, or t final minus t initial. Same thing goes for this, except we are going to be using the vector r to describe position. So the velocity average would then be our delta r over delta t. So in our example problem, we actually had some r as a function of time. Well, we could find an r final and an r initial at some t is equal to t final and some t is equal to t initial. Well, we could take those, r final minus r initial, and divide it by our time interval. That would give us our average velocity. Okay. We also saw we could describe a vector r as the change in x in the I direction, plus the change in y in the j direction, plus the change in z in the k direction. If that's the case, then we can say, let's divide this whole thing by delta t. We're not going to call that r anymore, we're going to call that our v average, velocity average. And we can simplify that a little bit more if you wanted to. You could say, and this comes in handy because you actually will be looking at the motion in each direction, right? We need to know about the motion in the x, the motion in the y. We have to break it into components, and then we'll put it back together. So if we broke up the x motion, it would be delta x over delta t in the I, and delta y over delta t in the j, and delta z over delta t in the k direction. Alright. And don't forget, each one of these deltas is a final minus initial. So what does that mean? We need 2 points at least for each x, 2 points for each y, and 2 points for a z coordinate in order to find an average velocity over that time interval. So for example, we have, it says a particle moves through a displacement and they say the displacement is given to us as a vector, and we could say delta r, that's the displacement, right? Not r, but delta r, is equal to some 12 meters in the I direction plus some 1.5 meters, 3 meters in the k direction. Alright, they say that this all happens in 2 seconds. If that's the case, then we can take our velocity average definition and say if it's delta r over delta t, well, we have delta r now. The key is knowing displacement literally refers to delta r, right? So delta r would be our 12 in the I direction and the 3 in the k direction. And we divide that by the time interval of 2 seconds. Okay, well these are divisible. We can reduce this a little bit, and we get a vector answer as an average velocity of 6 in the I direction, so 12 divided by 2, and 3 divided by 2 is 1.5 in the k. And that's all going to have units of meters per second now. Alright, we're going to talk a lot more actually about instantaneous velocity. They're both very useful, but we're in calculus. Instantaneous. Since we're in calculus, or since we know calculus, we can actually find the slope of a function and figure out what the velocity is at any instant using calculus definitions. So let's find the instantaneous velocity of something. Oh, the instantaneous velocity is literally just the derivative with respect to time of our position function. So what's the slope? And just real quick, if we wanted to look at a graph of what's going on, maybe we have some path that goes like this. At some time t, we have our position at 1, and then at some other time it moves over to position 2. We would draw and locate these as some r1 vector and some r2 vector. Their change in position would be equal to subtracting them, and we would get a delta r. Okay, what's next? We call this a path equation too. That was the path, and this is x and y. And we can locate it at 1 and 2 with position vectors r1 and position vectors r2. So if we wanted to know what the instantaneous velocity was at 1, guess what? We're just literally finding the slope right there. The slope is equal to the instantaneous velocity if we're looking at a position graph. Okay, and go ahead and label that an origin. So let's take this one more step for some clarity. The velocity is the time derivative of its position vector r. So remember we had a position vector r is equal to some x amount in the I direction, some y amount in the j, and some z amount in the k. This is the position vector. We'd have units of length, and we can literally just take the derivative of this thing. So I'm going to take the time derivative of the whole thing. And that whole thing is in meters. Alright, well what do we get? We get dx dt in the I direction, dy dt in the j direction, and some dz dt in the k direction. So what does that mean? Well, kind of like the rabbit problem, if we have position as a function of time, so we can get from position to velocity as a function of time by taking the time derivative. And same goes for the j and k components also. Well, we can rewrite this velocity vector then, because these could be evaluated at some time t and actually give us back a number. The velocity vector would be equal then to the velocity in the x direction plus the velocity in the y direction plus the velocity in the k direction, and that's z. Alright, so all those are actually important. We will be using them. And if you ever have to, we can find each component as dx dt. The y component as dy dt. And the z component as dz dt. So if we were given let's say we had the rabbit problem again. They gave us the position as a function of time as a negative 0.31 t squared. And this was for the x component. Remember they gave us x and y, plus a 7.2 t plus 28. Well, if I wanted to find the velocity as a function of time, I can just take the time derivative of this whole thing. And that would be our velocity in the x direction. So we need to get rid of the vector sign on that because we're looking at the component. Well, taking the derivative would get me a negative 0.62, still multiplied by t, plus 7.2, and that thing drops off. We'd have to look at the y direction also. If they give us r in the y, the position in the y direction as a vector as a function of time, and in this problem is 0.22 t squared minus 9.1 t plus 30, and all that's in meters. All this is in meters. If I want to get to the velocity in the y direction, we're going to take the derivative with respect to time. So I get 0.44 t minus 9.1, and that would all be in meters per second. Okay, we could evaluate that at any time t then. So they want, let's see, $15 again. It'd be smart to take this and make a velocity vector from it, where the x component would be this whole negative 0.62 t plus 7.2. That's all in the I direction. And then we can take this whole thing and throw it in for the y component. 0.44 minus 9.1. And that's all in the j direction. If we wanted to evaluate this whole thing at time is equal to 15 seconds, so v at t is equal to 15, ends up being a negative 2.1 in the I and a negative 2.5 in the j. And that's all in meters per second. So let's make sense of that vector real quick. This is going to be, if I drew quick origin, it's going to be something in the third quadrant because it's going to go left 2.1 and down 2.5. So something like this. Your angle you could find by using 2.5 over 2.1. That would give you this angle. Measured from this axis, our theta would be equal to that theta 1 plus 180 degrees. And theta 1 would be equal to the tangent inverse of the opposite over the adjacent, 2.5 over 2.1. And we could find the magnitude of v by the square root of 2.1 squared plus 2.5 squared. So I get the velocity is equal to 3.3 meters per second, and it's at an angle of negative 130 degrees. So negative would be measuring from there.